Hi, everybody. My name is Simone Blasi, and I'm a postdoc at Daisy Hamburg. Today, I'm going to be talking about QCD axion strings and their role as seeds or impurities for cosmological phase transitions. This talk is mostly based on this paper here in collaboration with Alberto Mariotti. Um, so the focus of our meeting is the early universe, and then let me specify how early is our dynamics taking place. So for the rest of the talk, we are gonna be focusing on this temperature range from around 100 GeV, corresponding to the electroweak scale, up to possibly very high temperatures of the order of 10 to the 10 GeV. And this value of Fa, or these very large temperatures, are of course connected to the Peccei-Quinn solution to the strong CP problem, where Fa indicates the QCD axion decay constant. And in this talk, we will actually consider a scenario where the U1 global Peccei-Quinn symmetry is spontaneously broken after inflation at a temperature which is of the order of Fa. And as it is very well known, such a spontaneous symmetry breaking pattern implies the formation of topological defects known as cosmic strings, where the axion fields winds by 2 pi around the string, whereas the radial Peccei-Quinn mode interpolates between 0 at the center of the string and Fa at distances much larger than the string core, which is of the order of the inverse mass of the radial excitation. These objects, cosmic strings, are very interesting and have been studied extensively, in particular in connection to the production of axion dark matter and also gravitational waves. In this talk, we will take a slightly different perspective, and we will consider the interplay between these strings and the standard model Higgs sector, so namely the interaction with the Higgs boson. So let me give you already, let's say, the main message of this talk, which is that the formation of axion strings at the time of the U1 Peccei-Quinn breaking scale can actually alter significantly the thermal history of the electroweak symmetry and also the dynamics of the electroweak phase transition, okay? And this is the case already in the simplest realization of the QCD axion, namely the KSVZ model. And this is due to the fact that the model naturally contains a renormalizable portal interaction between the Peccei-Quinn scalar and the Higgs field, which is allowed by all symmetries, and actually it is necessarily generated at one loop because the Peccei-Quinn sector, of course, talks to QCD and therefore with the Higgs boson. And the dynamical explanation of the effect of axion strings on the Higgs is the fact that the modulus of the Peccei-Quinn field actually vanishes at the center of the string, and therefore, because of that, the Higgs mass and therefore all the dynamics of the Higgs field can be significantly different at the string core compared to anywhere else in space. So, if we consider the basic QCD axion string that I was showing before, the presence of this portal with the Higgs can actually induce two different effects. The first one is the possibility of breaking the electroweak symmetry at temperatures which are actually much larger than the electroweak scale. And in addition to that, the Higgs can actually develop a condensate along the string core whose value can be orders of magnitude larger than the today value of the Higgs condensate, so much above the electroweak scale. And the dynamics of breaking the electroweak symmetry on the string actually happens already within the standard model Higgs potential whenever one takes into account the portal coupling with the Peccei-Quinn scalar. And the second effect that can actually take place is the possibility of triggering a bubble nucleation along the axion strings. And this effect actually requires additional modifications to the standard model Higgs potential such that the electroweak phase transition is first order. So whenever you consider, however, a first order electroweak phase transition in the background of axion strings, one finds that nucleation can actually take place along the string with a different nucleation probability, and therefore this uh, can change a lot the dynamics of the phase transition itself. And so in our work, we have mostly focused on characterizing these two scenarios and providing the details of these dynamics depending on the portal coupling of the Higgs and the Peccei-Quinn field and the mass of the raw scalar. But let me also give you some outlook or, if you want, possible implications um, of these dynamics. So in the first scenario where, let's say, the electroweak phase transition is the one as in the standard model, so basically the standard model plus the Peccei-Quinn solution to the strong CP problem, the presence of this large Higgs condensate forming on the string at temperatures much above the electroweak scale can actually induce a modification of the dynamics of the string network due to the fact that now all the standard model particles will scatter off the axion strings because they now include a very large Higgs core. And if the dynamics of the network is modified, this will also consequentially induce modifications, for instance, in the axion production and perhaps also of the collapse of the network at the QCD scale. Whereas in the second scenario, where we have a first order electroweak phase transition, these dynamics can also be drastically affected. And in particular, we will now have the nucleation of non-spherical bubbles, which will actually percolate, or if you want, merge along the string length, and then expand as a very large horizon size, let's say, tubes. And it would be very interesting then to study the implications of these dynamics in terms, for instance, of gravitational waves and baryogenesis, given that the wall velocity in this case can actually be different than the standard homogeneous bubbles. All right, so this is, let's say, the main message of the talk. Now let me fill in a bit the details and also present in detail our analysis. So the central object of our study, as I said, is basically the QCD axion string. And this object follows directly from the U1 Peccei-Quinn global symmetry of our theory, where the axion is the associated Goldstone boson after its spontaneous breakdown. And it turns out that in the broken phase of this theory, string solutions are allowed where the axion field, basically the phase of the complex Peccei-Quinn scalar, winds by 2 pi around such a string configuration. And as I mentioned before, the radial field interpolate between 0 at the center of the string and FA very far from the string. So this coordinate r is simply the distance from the string core. And most of the variation of this scalar field happens on scales of order 1 over m rho. And as you can tell, given the fact that the radial mode vanishes at the center, this means that at the string core, the theory actually sits on top of the maximum of the Mexican head potential, which indicates that there is actually a very large energy density localized on the string, which translates in a string tension, which is typically indicated by mu, which can be very large, of the order Fa squared. And if you want, it represents the string mass per unit length. Actually, the tension of this kind of string, given the global nature of our Peccei-Quinn symmetry, is log divergent with let's say, with the IR cutoff of the theory, but in a realistic network, this log growth will be cut off, let's say, by the neighbor string. And yes, so let us then consider the minimal implementation given by the KSVZ model. And as I was telling before, the main ingredient is the presence of a portal coupling between the Peccei-Quinn scalar and the Higgs. And therefore, you can imagine of the full potential, including such a portal coupling, and then the electroweak potential for the Higgs and the Peccei-Quinn potential for the Peccei-Quinn scalar. As we shall see, what actually matters is not so much the size of the portal coupling kappa, but it's the ratio between the portal coupling kappa and the self-interaction of the Peccei-Quinn field. And this is kind of important because it tells us that even if the portal coupling is very small, this can be compensated by a very small portal coupling. So it is effectively the ratio, the only thing that matters for the dynamics, as we shall see. And so once the portal coupling is taken into account, one can show that the theory has more string solutions than the simple Peccei-Quinn theory without the Higgs. And in this slide, I'm showing the typical profiles. So on the left, I'm showing the profile for the radial component of the Peccei-Quinn field, and this basically shows that this one is really always the same. It doesn't change among the different string solutions. But if we then look at the Higgs profile, we can see that on top of the standard, let's say, solution where the Higgs is trivially vanishing everywhere, there exist solutions where the Higgs field actually grows towards the string core. And it can reach values which can be much above the electroweak scale. So now the question is how we can predict the formation of this type of string profiles and how their presence can influence the electroweak phase transition. And it turns out that the best way to study this problem is by referring to an effective field theory approach, which actually takes into account, or if you want, it exploits the fact that there exists typically a large hierarchy of scale between the Higgs mass and the mass of the radial Peccei-Quinn field. And it turns out then that one can basically integrate out the string, the axion string, as well as the massive radial excitations in favor of in favor of an effective field theory where the only dynamical degrees of freedom are the Higgs and the axion. And this effective field theory is actually very simple. It includes only two more additional operators. One of them is the standard axion Higgs portal, which is a derivative interaction. And its strength, as I was mentioning before, is controlled by the ratio of kappa over eta. And on top of that, an additional operator that knows about the presence of a string, which can be written in terms of a Dirac delta, localized contribution to the action. And if we look at this effective field theory, we can see that it actually contains an explicit dependence on this epsilon, which is of the order of the inverse rho mass. And all that this delta does is basically to impose a batching condition on the Higgs field at scales of the order of the string core, which is again 1 over m rho. And let me also comment that the axion Higgs portal is typically considered subdominant due to the fact that it is effectively a dimension 6 operator. But in the stream background, this is completely compensated. And therefore, if you now consider an effective field theory around the strings, this operator is actually very, very important and is unsuppressed, actually. So at the end of the day, all the effects of the axion strings on electroweak physics can be captured by just one operator and a matching condition for the Higgs. Now, a very important role in this dynamics is played by the effective mass of the Higgs along the string. And this can actually be evaluated by studying a small fluctuation of the Higgs field in the string background. And we can actually set up the problem, indeed, as an eigenvalue equation, and solve for the spectrum, namely the mass of the Higgs excitations, taking into account that we, of course, need to respect this boundary condition due to the presence of the string. And it turns out that this equation can actually be solved analytically within our EFT and within the approximations which are related to that. And the result in the end is actually very simple. So the effective Higgs mass on the string turns out to be the 4D mass, or if you want, the standard mass that the Higgs has very far from the string, minus a correction which knows about the UV scale of the string squared, so the mass of the rho scalar squared, times a suppression factor which takes into account the strength of the portal interaction. And of course, as you can see, in this form, with this functional form. So as you can see, if we now switch off the portal coupling, this contribution will vanish. And with this expression at hand for the mass of the Higgs, one can actually derive a very simple condition for when the axion strings will develop a Higgs core. And this is completely equivalent to just requiring the mass of these fluctuations to become negative, indicating that they, of course, want to grow. And by simply finding the point where the temperature at which this mass becomes zero, we can predict the temperature of formation of the Higgs core. And so now let me go back to the two different scenarios I was mentioning at the beginning, starting from the case of the standard model plus the Peccei-Quinn. So just the standard model Higgs potential plus the axion strings. And so in this case, we can actually, by the formula above, evaluate as a function of kappa over eta and of the mass of the rho field at which temperature the Higgs core will form. And as we can see from this plot, in this white region, temperature at which the core forms is the same as the standard temperature for the electroweak phase transition, indicating that actually the strings are really decoupling. They are not playing any particular role. But if we now increase our portal coupling or the mass of the rho, we can find that this temperature, which is indicated by TR, the temperature which the core forms can be orders of magnitude larger than the electroweak scale, as I was saying at the beginning of the talk. And at the same time, we can also calculate what will be the value of the Higgs field exactly at the center of the string, again, as a function of kappa over eta for different values of the rho mass. And as we can see, this core can be, again, several orders of magnitude larger than the 246 GeV value of the Higgs field today in the homogeneous space. Finally, let me also discuss the case of a first-order phase transition independent of the axion strings. And here we are just considering a toy model for a first-order transition by including a cubic term for the Higgs, but this dynamics is actually generic to any model with a realistic model, for instance, with the extended scalar sector, which would have a first-order phase transition. And what happens is actually the following. I mean, if we think of nucleation as happening very far from the strings, this will have a certain energy associated to the critical bubble, which will tell the nucleation probability. But if we now consider this nucleation process along the string, of course, if we set the coupling to zero, there will be no modification. But as soon as we turn on some portal coupling between the Higgs and the Peccei-Quinn field, we will find that the critical bubble has less and less energy, and at the same time, it will have a modified shape elongated along the string axis. And for some critical value of the coupling, the bubble will be typically one dimension. And in practice, what we do, we evaluate the nucleation probability along the string via three different methods that I'm not explaining in detail, but you can find in the paper, to show that this nucleation is actually faster than the homogeneous one for any value of kappa over eta. And here on the right, I'm actually showing the shape of the critical bubble for this benchmark that we can calculate precisely. And of course, it matches the shape I was showing in the various cartoons. And as I said, this will imply the expansion of bubbles, which will first merge on the string and then will percolate the universe via these tubes. All right, I think I will leave here my summary and outlook. Thank you very much.